So let me thank the organizer for inviting me in such interesting place with a diverse community. So what I'm going to tell you today, some recent work that we are doing with the cuprate superconductor, and that inspired by Moiré physics in 2D materials, we are exploring substrate engineering to tune the ground state of ITC superconductor. And the work has been done at Chalmers, and particularly from my two PhD students, Eric Valberg and Riccardo Paia. But we got a lot of help from theoreticians, from Get Sabelt from Brandenburg University, for Sergio Caprara, Marco Grilli. I would like your analog.
He's there.
Ah, he's there. Yeah, I'll try to be kind. So with us, with Sergio Caprara, Marco Grilli, and Di Castro from La Sapienza, and we got a lot of interesting collaborations with Giacomo Ghiringhelli and Lucio Bragovic for RIX measurements. Okay, so briefly, the archetypal ITC superconductor is the YBCO. Why it has been studied so extensively is because it can be quite easily grown into films. So you have three perovskite cells, one on top of each other, and the parent compound is a MOT insulator. And by adding oxygen in what are called the chains, one can induce superconductivity. So most of the physics happen in this copper oxide plane, and when you have the oxygen, you have transfer of electrons from the copper oxide plane into the chain, and this gives holes and gives conductivity. Why they've been well discovered in 1997, as Claudia pointed out. Why it has been so difficult to progress in this field? It is because these materials you can change the doping, but you change also the crystal structure. So it is not like 2D materials that you apply gate and you can retrieve the interface diagram. Here the carrier density in the plane is 5 × 10⁻⁴, so it is really difficult to tune gating, so they are only marginally tunable. The thing is, as I said, that the parent compound is an antiferromagnetic insulator, but then you add oxygen in the chains and the superconductivity sets in. You see here the dome. But close to the antiferromagnetic insulator, you have a phase that it is called the pseudo-gap phase, where you are missing state at the Fermi energy. And then you have a pseudo-gap that it is doping dependent. But within this pseudo-gap, you have also other local orders. You have charge density waves, so periodic modulation of charge into direction. There have been hints of loop currents. And so this is an anomalous state of matter. And what you have is you have competition between orders, like if this is a charge density wave, and when the charge density wave is maximum, you get a depression in the superconductivity. The end point of the pseudo-gap is P star, that is thought to be a critical point. And this is because the normal state that emerges from this P star has very anomalous properties, and we will hear more from Silke. So, as I said before, the normal state corresponding to this doping is what is called strange metal. And which are the properties? You are missing quasi-particles, so if you make ARPUS, you don't see the quasi-particle peak. And the most striking one is the T-linear dependence in 3 order of magnitude temperature range. And you can get that the extrapolation of this linear behavior goes to 0. This is really, really anomalous. And if you apply magnetic field to suppress, you continue to observe this T-linear behavior. So it is something extremely robust. However, as I said, this happens at the strange metal phase. So above this P star, when you go and increase the doping, you recover the conventional Fermi liquid. So you have Fermi liquid, strange metal, and here this is what is called pseudo-gap metal. And what happens to the R versus T, you have linearity here, like you get in at higher doping, and then you have deviation from linearity. What breaks this strange metal phase was up to a couple of years ago still a question. This strange metal, we've heard, it's not peculiar only of ITC cuprates, but there are heavy fermions, there is magic angle graphene. So it is something that comes out in strongly correlated materials. And in addition, in the strange metal phase, in addition to these properties, one gets also fluctuation of charge that we call the charge density fluctuation, and that we discovered a few years ago. So it is also a peculiar state of matter. The way that I said you before is that you have this T-linear that extends for several order of magnitude, even when the mean-free path is comparable with the distant interatomic distance. And this is a further, I can say, hints that the quasi-particle picture is breaking down. But if one takes the usual Drude formula and one takes the transport time, what has been proposed is that if the transport time is just depends on temperature and on natural constant h by kb, then one can retrieve this linearity resistivity, and one has started to talk about Planckian time, and that all this physics is related to strong entanglement between electrons. Okay, so this strange metal is not unique of ITC superconductors, but is also found in other materials like magic bilayer graphene. And in particular, well, we've heard a lot. You have two graphene layers, you twist, you quench the kinetic energy, and you are in interaction-dominated system with flat band. And surprisingly, the phase diagram of these materials has quite some peculiar resemblance with the phase diagram of ITC. You have the superconducting dome, the strange metal, and correlated insulator. However, what is very peculiar here is that the strange metal is precursor in magic angle graphene of an insulated phase before superconductivity takes place. In ITC, at the optimally doped, where TC is the highest, one gets that strange metal is precursor of superconductivity. So there are some difference here. However, flat bands have gotten so much attention because essentially if you have the BCS, the TC is exponentially dependent on the product between density of state and interaction. Instead, in a flat band system, you can get that the TC becomes linear with interaction. So you could boost, in principle, superconductivity by using the strong interaction and flat band. But superconductivity, as we heard the day before yesterday, is not only, it doesn't require only pairing, but it requires also global coherence. And this is given by the superfluid weight. But in flat band, we have that the effective mass, even though this is an approximation, as we discussed with Marco, the flat band is infinity, and then what one gets is that you don't get a superfluid weight. So in principle, if you have a flat band, you have that your electrons are immobile, so you need a finite superfluid weight to get superconductivity. And then it has started all the field of quantum geometry with quantum metric that would give a finite mass to this. If this applies to magic angle graphene or other system is still to be discussed. However, looking at all these sorry, it wants to update. So, looking at all these evolving field, what about ITC? Do they have portions of flat that are suspiciously flat? And indeed, they have. We have also seen from the a talk of Claudia that there are other systems with this fun of singularity at this point. And if you read papers 30 years old, they did think about the flatness here in the 0 pi direction as a possible origin of ITC superconductivity. Nevertheless, why this thing was abandoned? Because usually this van of singularity becomes closer and closer to the Fermi level when you go at the overdoped. So when you are reducing the superconductivity, and this is one of the reasons somehow it was abandoned. But what we want to do now is we want to tune this van of singularity in our films and see how the properties are changing by changing the position with respect to the Fermi energy. And this is substrate engineering that I was telling before. Okay, so the first thing that you need is to establish a platform of thin films as a function of doping that when they are kind of thick, they reproduce the same properties of the single crystal, so you have the same phase diagram. And then you need to have them untwinned. You remember that oxygen are in the chains, so you need to have chains that are preserved on the substrate. So this is the phase diagram that we have for thick films of 30, 50 nanometers that has all the peculiarity that I showed before that is similar to single crystal. And then you go to 10 nanometer films, or even lower. We can grow 5 nanometers in films. The first thing you do, you try to understand what is how does the geometry changes. And here we see as a function of thickness that the axis is almost constant, the b-axis is extended, so you have tensile strain, and the c-axis is reducing. Then you take these films and you make an angular dependence. So you can pattern whole bars or nanowires as a function of the angle. And you see how the properties are changed. And this is quite surprisingly. This is at underdoped films, where you have depression of the superconductivity because there is competition with charge density wave. And you see the resistive transition along A and B, and they look pretty much the same because you have that the chains are quite disordered at this doping, and they contribute not so much to the transport. So you have that the slope of this resistive transition along A and B are the same, and the deviation from linearity, so where the strange metal is breaks down the temperature, is almost the same. But if you have the same doping and you go to 10 nanometers, physics changes dramatically. So you have a strong anisotropy in resistivity, even at room temperature. You have that the strange metal in the B direction extends to much lower temperature, but very significantly here is the slopes in a two resistive transition. They are very different. And if you take the Boltzmann formalism, you get that the velocities along A and B becomes, the Fermi velocity becomes different. So you go from this circular Fermi surface to a nematic Fermi surface. And this nematic Fermi surface, most probably, it is the origin for all this, as I will try to convince later on. So we have, this is simple transport. Now, what about the rest? We have all these other orders that are playing a role. Does charge density wave changes? And what we did, we took Rix measurements on these samples. So we took our thin films, went to synchrotron, and we measured Rix. Rix is a technique photon in and a photon out, and is resonant. So you are exciting from the core level of the copper in copper oxide plane to the valence band. And you can take the intensity of the emitted phonon as a function of the energy, and you have the big dd orbital excitation corresponding to this transition. But then at zero energy, you have a peak that is maximum at 0.3. And this peak depends on the temperature. And this has been the first demonstration of charge density wave exists in these materials through RICS. There were indications with other techniques, like with neutron from Ghiringhelli group in Milano. So we took our sample and we went at the synchrotron. What is relevant here to recall is that charge density waves are bidirectional. You can have along A and along B in single crystals. What happens in our films? As I said, the surface is nematic. And what happens is that if you take the charge density wave along the A axis, you see that in thin films, which is the rose curve, is very suppressed compared to 50 nanometer films. Instead, if you take along the B axis, you see that the charge density wave is the same in 10 nanometers and 50 nanometers. So what you get that the ground state is modified, so you have this nematic Fermi surface. In addition to this, you have that the charge density wave becomes unidirectional, and this allows to restore the strange metal phase along the B-axis. So you have a quite strong connection between breaking down of strange metal phase and the charge density wave. So this is what comes out from here. Then, well, what are so peculiar in this film? What did we do to the films to get such high anisotropy? Before growing the films, the substrate were reconstructed. So what we had annealing at high temperature to get that the film deposited on top would have been untwinned. So, and this is the morphology of the films. This is a IFM picture. If you take a cross section, you get these triangular shapes of the substrate, and surprisingly, the periodicity of these facets that are unidirectional, it is very close to what one gets for the Mori materials. So this is the surface for the MGO that has been reconstructed, and this is the surface for STO that is vicinal cut to get the untwinned films, and you get this step-like picture. But what is surprising here is that if you take peak force measurements, you get a very different contrast across the samples, and you have this dark region at the tip of the substrate, where you have tips of the substrate on the film. And what happens then, what we believe is that here you have uncoordinated atoms with dangling bonds, and they strongly bond with the YBCO, making different materials. You could get also on stronzotitanate, but these regions here, they are very tiny, corresponding only here where you have uncoordinated atom in the substrate. And because of this, if you take a resistive transition of films 10 nanometers on stronzotitanate, the same doping, what you get is that is light anisotropy here, because you still have the chains, but the slopes are the same along A and B. So this is this tells us that that you have tiny variations of the properties of the films because of this step. Instead, here you are completely completely changing the property of the materials. But then, considering this periodicity here, what one get, you get one periodic superlattice that is imposed to the YBCO. So the physics that you get essentially, this is analogous to imposing a Moret superpotential to these films. Okay, this is the normal state properties. What happens to superconductivity? Then this is 50 nanometers films. These are 10 nanometer films. And you see that the TC onset is increased almost 20 Kelvin, going from 50 to 10 nanometers. And you can make it as a function of the doping, and what you get, you are recovering the parabolic dome here in 10 nanometer films. And this is up to 0.12, where then charge density wave becomes weak, and it doesn't compete more with superconductivity. So even though you have removed in one direction, you will not get any increase, because this is not due, this depression here is not anymore due to charge density wave. Okay, so this is the TC. And what happens to the HC2? Well, something interesting happens also to HC2. These are the resistive transition for 50 nanometer film, and this is for 10 nanometer film as a function of magnetic field. And then you can retrieve the T dependence, HC2 T dependence by considering for every field the temperature at which the resistance is 1/2 of the normal state. And then you can, this we did in our standard PPMS up to 15 Tesla. But nevertheless here you do see that the slopes are completely different for 10 nanometers and 50 nanometers. But then we made the experiment considering vortex melting transitions, and we get also that you see the concavity for 50 nanometers and for 10 nanometers at much higher fields, because we went to 50 Tesla, are completely different. Nevertheless, the field that you can extrapolate as 0 is the same for these simple measurements and vortex melting measurements, and it is much higher in 10 nanometers compared to 50 nanometers. Okay, so what we did, we needed a test experiment to see if the HC2 fields for our thin films, which are conventional bulk, I would say, as a function of doping, was following the same dependence as for single crystal. And these are the rose curves here, rose point here, and the dashed one is what has been measured for single crystals by Taillefer group. And you see that we get a pretty close dependency here. And this is interpreted why the HC2 is depressed as a function of doping. This is has been interpreted with a competition with between charge density wave and superconductivity, because this charge density wave nesting, quasi-nesting, removes states, and there are less states available for superconductivity. You have a reduced TC and reduced HC2. But for 10 nanometers at the same doping, you have the extrapolated HC2, which are 60 Tesla higher. So what is the origin of this increase? Is it the charge density wave? Because in our thin films, now we have that the charge density wave is effectively, the volume is reduced because it has become one-dimensional, or it is something else. Essentially, we believe that the charge density wave and the increase of HC2 are kind of disentangled, because this is the increase in TC in thin films as a function of doping, and we plot also the increase in HC2 compared to thick films in our thin films as a function of doping. And you see that the maximum increase in the HC2 happens here at doping, where you don't get a strong increase yet of the temperature, of the superconductive temperature. And this somehow tells that the two things are kind of disentangled. But then why do we get this? And the reason we believe is that the surface is nematic. So we have these tips here. the HC2 is inversely proportional to the product of the Xi. But within the Gibbs-Bolander formalism, the Xi is inversely proportional to the mass. So here you have that the bands are flatter. So you have a higher mass, and this higher mass gives lower Xi, and then you get a higher HC2. So this is a consequence of this peculiar Fermi surface that we are exploring in our films. And this goes almost to the end, because what we have further studied is we wanted to understand if in our film the analogy with matching angle graphene would have been pushed forward. I told you that in these materials, in the magic angle, you have strange metal, correlated insulator, and superconductivity. In our film, what we have is that you have linear inti precursor, strange metal precursor superconductivity. But will we get anything like this in our thin films? And the answer is yes. When you go to very low doping, because what I showed you before, it was at 1/8 doping, so intermediate. But if you go towards the Mott insulator, what we get similar R versus T than what has been obtained in magic angle graphene. So you have a linear anti-resistivity in insulating behavior before resistivity, before superconductivity sets in. And even more interesting, what you get is that at this low doping, the resistivity along the B-axis becomes much higher than the resistivity along the A-axis. You are essentially getting a completely different material. So take-home message is that by nanostructuring the substrate, one gets a phase diagram that has been completely reshaped. You have that deviation from the linear behavior happen at temperature much lower along the B-axis. You get an increase of TC and HC2. Charge density wave become unidirectional, and also normal states in terms of what you would expect for the resistivity of A and B is changed at low doping, because B becomes much higher than A, so you have a completely new material. So what is next? And this is my last transparency. What is next? Well, this reconstruction happens naturally when you anneal the substrates, because we want to get untwinned films. But the next step is just to pattern any possible geometry one wants, like in the same way as Alex has shown for gallium arsenide, and to try to explore what these geometries that can have symmetry and also distance between steps at will, what will do from the point of view of the band structure. And what is happening here, we made some, our colleagues made some preliminary investigation. And what you have is that because of this Moiré superpotential, you get that depending on the sign of the substrate voltage that you are imposing, you can split your band in several mini bands. And this mini band, if for instance the potential is positive, they become even flatter. So you can tune your Van Hove singularity closer or farther from the Fermi energy by imposing to the film any kind of symmetry that you want. But this is work in progress. And this is the group. It's in old pictures, but these are the two people that have been mostly working on this project. And I thank you for your time.